The clock is generated on chip using PLL, phase lock loop. So here we have the PLL which combines the spectral purity of the crystal with the frequency flexibility of the voltage controlled oscillator to produce a stable clock. Fs is n times f naught, where n is an integer and f naught is the reference crystal frequency. So this is how clock is generated on chip, and this is a basic integer n PLL, and to improve the resolution we might have a pre-divider and a post-divider as shown here. So the conventional method to generate the clocks for the different IP cores is to use a dedicated PLL for each IP core, as shown in the figure here on the left, the conventional approach. And as we saw in the last slide, we might use a pre-divider and a post-divider to get the exact frequency required for a particular IP core. As more and more IP cores began to be integrated, the need for flexibility, that is to be able to attach a core in a plug-and-play manner without affecting the whole interconnect network, necessitated making the operating frequency of the IP core independent of the interconnect network. This decoupling of the functional behavior of an IP core from its communication behavior is advocated in both bus-based and NOC-based SoCs. Consequently, the IP cores began to be classified as either functional cores or interconnect cores. Functional cores are the ones which perform the arithmetic functions, the transform functions, video, graphics processing, encryption, decryption, etc. And the interconnect IP cores are the cores which are responsible for forming the I/O interface between the SoC and the external world. They may be cores like the DDR controller IP, the USB host controller IP, the HDMI, etc. The functional cores have some flexibility in their operating frequency, while the interconnect cores usually require a rigid operating frequency. The average number of IP cores in emerging SoC designs is around 100, and it's expected to increase in the future. The large number of IP cores and their diverse operating frequency poses a complex clock generation problem in the SoC design. Because, as we saw in the conventional approach, because we use a dedicated PLL to generate the clock for each IP core, the more the number of cores, the more the PLLs will be required. For example, Texas Instruments DaVinci SoC needs 15 on-chip PLLs. If it grows at this range with the increase in number of IP cores, there may come a day when the clock generation becomes intractable. Hence, we need a methodology to generate more unique frequencies using minimum number of PLLs, because if we minimize the number of PLLs, we're going to minimize the hardware and the power consumption. Since functional cores can be operated at a range of frequency below their maximum operating frequencies, we propose a methodology like this, where if we have 4 cores whose maximum operating frequencies are 60, 210, 460 and 625, why not operate them at 54, 192, 432 and 576? If we can operate them at those frequencies, then the clocks for all those 4 IP cores can be generated by a single PLL, generating the LCM of those frequencies, that is 1728 MHz, followed by clock dividers. We can have integer clock dividers for after the PLL to generate the individual frequency required by the IP core. Given the set S, the set of the maximum operating frequencies of n IP cores, and SM, a lower limit on the operating frequency, maybe 10% below S, the problem is now to find the frequencies between S and SM whose LCM is minimum. Assuming the frequencies of the 8 IP cores is in megahertz, the LCM obtained by the OOF algorithm is 10,800 megahertz. A PLL to generate 10.8 GHz clock is not only difficult to design but consumes exorbitant power. Hence, we use another algorithm called the optimum partition algorithm to split the OOF set, optimum operating frequency set, into subsets so that the LCM of each subset is low enough to be generated by a practical PLL. 2 PLLs followed by 8 clock dividers consumes lesser power. We have done Monte Carlo simulations to study the effectiveness of our algorithms.